configuring and testing electronic components. Upon completion of this exercise, participant will acquire the ability to identify the electronic control unit (ECU) and engine scanner. Additionally, they will develop skills in thoroughly inspecting and understanding the electronic control unit in the context of automotive technology. Recognize and name essential components of the multi-point fuel injection (MPFI) system and sensors in an automobile, such as the ECM, flywheel, oxygen sensor, and ignition coil. Demonstrate the ability to physically locate each component on an actual automobile. This includes hands-on identification, aiding in practical application of theoretical knowledge.
Tools and equipments required: trainees toolkit, engine scan tool, a running condition of EFI vehicle, gloves, cotton waste, soap oil. Let us start by identifying the electronic control unit (ECU) and engine scanner. This session focuses on understanding and testing the ECU, vital in diagnosing and ensuring optimal performance of the vehicle's electronic control system. The first step in this procedure is choosing the service manual. Selecting the appropriate service manual for your vehicle is crucial as it provides accurate documentation essential for maintenance and repairs. Following the correct manual ensures precise guidance, promoting effective troubleshooting and enhancing overall vehicle performance and longevity. The next actions explain how to physically set up the scan tool. This involves connecting the test cable, making sure the ignition switch is turned off, and using the right cables and adapters to connect the diagnostic connector. Attach the accurate diagnostic connector. Link the scan tool's test connector cable to the diagnostic connector. Utilize the correct adapter if needed. It's important to note that OBD2 scan tool get power solely from terminal 16 of the diagnostic connector, eliminating the need for supplementary power connections, simplifying the setup process for users. After connecting, observe the scan tool's screen to ensure it functions correctly. Most scan tools conduct a self-check, alerting technicians to potential software or communication problems. This step verifies the tool's operational status and prompts necessary action for issue resolution. Now the tool needs some information about the vehicle. So all you need to do is to enter essential vehicle information into the scan tool. Modern OBD2 tools automatically retrieve VIN when the ignition is on, facilitating code checks. Older tools necessitate manual input of details like year and engine type, typically found in specific VIN characters, ensuring accurate diagnostics in both scenarios. Once the ignition key is turned to the on position, the scan tool checks for trouble codes and any detected codes are listed. The user. Here you can consider yourself as the user. So you will be guided to consult the scan tool literature or service manual to interpret these codes, crucial for pinpointing specific issues within the electronic control system. The subsequent step involves erasing the trouble codes, switching off and on the ignition to verify if the issue persists, and checking the engine indicator. Ensure the engine indicator is in off position. If not, there might be issue with the electronic management system (EMS). After completing the test, the ignition is turned off. and the scan tool connection is removed from the diagnostic connector. Sensors play a crucial role in vehicle electronic control systems. Sensors are devices that convert or transduce physical quantities. The process involves converting physical quantities such as mass, pressure, volume, temperature, or acceleration, referred to as measurements, into output signals, typically electrical, which are then used as inputs for control system. Let's get familiar with an understanding of the multi-point fuel injection (MPFI) system and various sensors in an automobile. Let's get this started by identifying the different sensors of the engine. Locate the engine control module (ECM), which is the heart of the operation and is in charge of running the MFFI system. Locate the important parts like the flywheel and the crankshaft position sensor. These sensors are positioned within the crankcase and crank pulley. These sensors are mostly utilized to monitor the injection timing and ignition timing of the engine, which are dependent on the speed of the vehicle. In order to do both qualitative and quantitative analysis and control as well as monitor efficiency. The exhaust manifold is the location of the oxygen sensor. The device is utilized to quantify the amount of unbound oxygen present in the emissions from an engine. This measurement is crucial in determining the optimal timing and quantity of fuel to be used. Mass airflow sensor. It measures the amount and density of air entering the engine at any one moment and is located in the intake manifold or throttle body on MPFI. For the engine's balance and proper fuel mass delivery, the data is crucial. Hall effect sensor. A magnetometer is a device utilized to quantify the intensity of a magnetic field. Its output voltage is directly proportional to the strength of the magnetic field passing through it. Hall effect sensors are utilized for many applications such as proximity sensing, location, speed measurement, detection, and current sensing. This sensor is responsible for monitoring the temperature of the incoming air and the coolant in the engine. When the temperature rises, the resistance decreases and the voltage output increases. This prompts the ECM to detect the issue and interpret the required power supply while sending a signal. Find the ignition coil, which is required to convert low voltage electricity into the high voltage electricity, which is required by spark plugs. Vehicle speed sensor. In order for the computers to control the torque converter, clutch lockup, shifting, etc., this sensor keeps an eye on the vehicle's speed. The sensor is found on the head of the speedometer, transaxle, or gearbox. Start by looking at the fuel system's common rail, pressure regulator, supply line, injector, and accumulator. Then move on to the fuel tank, electric fuel pump, and fuel filter. The location of the component can be found in the engine block, cylinder head, or intake manifold. It is utilized to detect vibration resulting from the engine's detonation. This information is highly valuable for determining the injection and ignition timing in diesel and petrol engines respectively. Explore the sensor network, which includes the idle speed actuator, the intake air pressure sensor, the throttle speed switch, and the engine temperature sensor. Finally, locate the spark plugs. This is very important for lighting the mixture of air and fuel in each cylinder.
Let's recap this topic. In this topic, you have learned that the first step in this process is choosing the service manual. Selecting the appropriate service manual for your vehicle is crucial as it provides accurate documentation essential for maintenance and repairs. Following the correct manual ensures precise guidance, promoting effective troubleshooting and enhancing overall vehicle performance and longevity. Hope you have a clear understanding of this. Do this exercise with help of your instructor. Thank you. Welcome to this session on inspecting and replacing defective gauges on the dashboard. In this session, we will cover the process of checking instruments and gauges for optimal functionality. By the end of this exercise, you will be able to verify that the instruments and gauges are working correctly, install new instruments and gauges.
Tools and equipments required: trainee's toolkit, multimeter, vehicle, materials required, cotton waste as required, soap oil as required, gauges as required, bulbs as required, wire as required. Let us start the session by examining dashboard instruments. Get ready to explore and understand the dashboard components. While starting the procedure, ensure that the vehicle is parked on a level surface. Parking on the level surface will guarantee stability during checks and maintenance. After parking the vehicle accurately, secure it by placing wooden chokes against the wheels. This precautionary measure helps prevent any unintended movement, ensuring stability and safety in the parked position. Now, apply the handbrake and assess the dashboard to confirm that the parking brake light illuminates as an indication of its proper functioning. This step ensures the parking brake is engaged and functional before further checks. Now, all you must do after securing the vehicle is to switch on the main ignition and check the dashboard for warning lights and instrument readings. This step ensures that all essential systems are working properly. Verify the proper functioning of critical indicators such as engine warnings, oil pump status, seat belt reminder, battery charging status, headlight and side indicator notifications, as well as safety and cabin temperature indicators. These warning lights serve as vital indicators of the vehicle's health and readiness for operation. The next step is to start the engine. Pay close attention to the RPM meter, fuel gauge and temperature gauge. The RPM meter measures the engine's revolutions per minute, indicating its operational status. The fuel gauge provides information about the fuel level, crucial for planning refueling stops. Simultaneously, the temperature gauge monitors the engine's temperature, ensuring it remains within optimal operating limits to prevent overheating and potential damage. Let us continue the session by checking defective gauges and instruments and replacing it. Start the procedure by starting the engine and inspecting warning lights on the panel boards. This systematic approach entails a carefully planned troubleshooting sequence to identify and address potential issues. If no warning lights are illuminated, The second step advises inspecting connections and bulbs, suggesting bulb replacement and addressing loose wire connections if needed. Subsequent steps involve checking and replacing defective components such as the RPM meter, fuel gauge, and temperature gauge. Moving the vehicle and verifying the speedometer during operation ensures a comprehensive assessment of RPM meter functionality. Note that the speedometer is also known as an odometer. In case of defects in the odometer and RPM meter, a thorough examination of wire and cable connection is recommended, with the replacement of any faulty gauge sensor wires. Now, with the thorough grasp of the topic, it's crucial to highlight the final step before concluding. This step underscores the significance of verifying the functionality of all gauges and warning lights after replacement. It not only addresses individual instrument defects but also emphasizes the necessity of the comprehensive system check to ensure the overall functionality of the vehicle's instrumentation.
Let's recap this topic. In this topic, you have learned that verify the proper functioning of critical indicators such as engine warning, oil pump status, seat belt reminder, battery charging status, headlight and side indicator notifications, as well as safety and cabin temperature indicators. These warning lights serve as vital indicators of the vehicle's health and readiness for operation. Hope you have clear understanding of this. Do this exercise with the help of your instructor. Thank you. Hello and welcome to the session on test temperature sensor, pressure sensor, potentiometer, magnetic induction sensor, camshaft sensor, camshaft position sensor. By the end of this exercise, you will be able to identify the appropriate testing procedure for the temperature sensor, evaluate the pressure sensor readings, demonstrate the correct usage of testing equipment for the potentiometer.
Tools and equipments required. Trainee's toolkit, multimeter, vehicle, one tray and banyan cloth. Let's begin this session by testing the temperature sensor. The coolant temperature sensor measures how hot the engine coolant is. It sends this information to the car's brain, that is ECU, which then uses it to improve fuel and ignition timing. To test the coolant temperature sensor, follow a systematic process. Start by opening the bonnet to access the engine component. Locate the temperature sensor. Mostly it is situated in the thermostat valve area. Now turn on the multimeter. Select resistance mode and you are ready to measure resistance. Ground the multimeter's black terminal and connect the red terminal to the temperature sensor, measuring its resistance. Proceed by turning on the engine, allowing it to run for 2 to 3 minutes to reach operating temperature. Remeasure the resistance using the same procedure. A significant point of analysis lies in the difference in resistance between the initial and warm-up status. If the contrast is greater than 200 ohm, it indicates the temperature sensor is in good condition, effectively responding to temperature changes. The next task is to test the pressure sensor. A fuel pressure gauge provides visibility into the fuel delivery system's effectiveness, ensuring sufficient pressure for optimal engine performance. Inadequate pressure can lead to inefficient engine operation. Various sensors such as air intake pressure, atmospheric pressure, vapor pressure in the fuel tank and fuel injection pressure sensors play vital roles in a vehicle's performance. Despite the distinct role of sensors, their testing procedure remains consistent. To start the test, first identify the sensor's location within the vehicle. Once located, use a multimeter. Set to the DC millivolt range for precise measurements. Now start to run the engine. With the engine running, the procedure continues by grounding the black terminal of the multimeter and delicately touching the red terminal to the sensor. If the sensor is functioning correctly, you can observe a voltage reading within the range of 200 to 400 millivolt. In case where no voltage develops, it indicates a potential malfunctioning. In this case, it is better to replace the sensor. The next test is the throttle position sensor, that is the potentiometer test. Throttle position sensor, potentiometer test evaluates the sensor on the throttle body, measuring throttle valve movements and transmitting data to the engine control module. The faulty component is a spring-loaded mechanism serving as a throttle position sensor (TPS). In its resetting state, the TPS emits a low signal voltage of approximately half volt when the accelerator pedal is not pressed. The TPS relays pedal position to the engine computer with higher voltage signaling and increased engine speed during pedal depression. A failing TPS may not trigger the dashboard check engine light, but a code scanner can unveil related trouble codes. Troubleshooting involves a digital meter set to DC voltage, jumper wire, and a needle or pin. The black meter probe connects to the battery negative or engine ground, while the red probe connects to the positive terminal. Inserting the needle into the TPS wiring allows voltage readings to identify the power supply wire, typically around 5 volts. This diagnostic procedure aids in detecting TPS issues, facilitating a comprehensive assessment of its proper functioning. The next sensor is the crankshaft position sensor. The crankshaft position sensor determines the crank's position and RPM. The engine control unit uses this data to regulate ignition and fuel injection timing, optimizing engine performance and efficiency. These sensors, known by various names like Hall effect sensor, CKP sensor, CMP sensor, pickup coil, magnetic pulse generator, and more. Let's see the simple procedure to test the crankshaft position sensor. Locate the sensor with yellow signal, black ground, and orange ignition wires. Check voltage with ignition on 12 volt on black wire to confirm battery connection. Use multimeter 20 volt setting, black lead on black wire. Expect 12.13 volt positive and 5 volt. Do not start the car. Turn on the ignition. For push start, position the timing gun until the lights come on. For manual, go to the second position. If the sensor is not installed, Turn off the ignition after confirming voltage readings. Use a device or alligator clip for testing without opening wires. Connect black lead to engine ground. Expect around 5 volt. Attach metal to the sensor. Voltage should drop to 0. Repeat for consistency. A normal sensor switches between 5 volt, no metal, and 0 volt with metal. Irregularities indicates a faulty sensor. Let us understand the working of the camshaft position sensor. Identify the engine type, especially in newer engines with 2 camshaft position sensors, one for intake and one for exhaust, which may vary in engines with variable timing. Turn the ignition switch to the second position to illuminate the dash lights without starting the engine, preventing potential damage to the engine computer and fuses. The camshaft position sensor typically has 3 wires: ground, power, battery voltage, and signal around 4.8 to 5 volts from the engine computer. Use a cost-effective voltmeter to probe and identify the ground, power, and signal wires. This tool aids in precise determination of each wire's function. Connect the sensor wires consciously, considering the potential risk of engine damage as part of the diagnostics process. Highlight specific wire colors for easy identification. Example: green for ground, blue with orange for signal, and a voltage carrying power wire. Confirm proper sensor functioning by measuring a voltage of approximately 4.8 volt with the probes connected. Introduce a metal object such as a socket near the sensor. Observing the voltage drop to 0 simulates the on-off behavior of the sensor, confirming its responsiveness to change in the camshaft's position. Let's get into topic of magnetic sensor. The ABS computer supplies a 12 volt reference voltage for the Hall effect wheel speed sensor. The sensor, featuring an internal transistor, responds to the reluctor or toothed wheel, generating voltage as metal teeth pass by. Hall effect sensor consistently produces a square wave signal, unlike magnetic sensors, maintaining a constant amplitude regardless of rotational speed. Manufacturers prefer Hall effect sensor due to their amplitude stability. To assess the sensor, measure reference voltage with a multimeter when the key is on, and compare the sensor ground to battery voltage to ensure proper functioning. Use an oscilloscope to capture the square wave signal with its frequency indicating wheel speed. Test the sensor with the connector, both connected and disconnected. If connecting the sensor results in a reference voltage loss indicating a short circuit, replace it. Always use the APS computer as the reference voltage source.
Let's recap this topic. In this topic, we have learned that the temperature sensor measuring engine coolant temperature adjusts fuel injection and ignition timing. The throttle position sensor potentiometer mounted on the throttle body measures throttle valve movements. The crankshaft position sensor CKP determines crank position and speed, influencing ignition and injection timing. Magnetic induction sensor, composed of an electromagnetic coil, is tested by connecting a multimeter between the sensor and the engine control unit ECU to check for voltage signals during engine operation. Hello and welcome to this session on performing a diagnostic assessment to identify potential causes and solutions for issues such as difficulty starting the engine, poor fuel economy, or suboptimal engine performance despite the engine cranking. By the end of this exercise, you will be able to understand the common reasons behind an engine cranking, identify potential causes for poor fuel economy in a vehicle, explore practical diagnostic techniques to pinpoint issues related to starting, fuel efficiency, and overall engine operation.
Tools, equipments and materials required. Trainees toolkit, multimeter, one diagnostic tool, vehicle lift or jack stands, fuel pressure gauge. The initial step is troubleshooting electronic petrol ignition system is when the engine cranks but fails to start. Let's begin with it. When encountering a scenario where there is no fuel in the tank, the first step is to address this issue by adding fuel and ensuring it is the correct type for the vehicle. If the issue continues and there is no fuse for the fuel pump, it's important to replace the fuse and ensure the replaced one is of the correct type. Moreover, if the fuel pump switching circuit and safety circuit are not working, it is essential to repair or replace the components of the pump circuit to restore proper functionality. If the fuel pump is not working, the best solution is to replace it. This involves installing a new fuel pump to ensure the proper functioning of the vehicle's fuel delivery system. A blocked fuel filter can also hinder fuel flow, necessitating its replacement to maintain an unobstructed fuel pathway. In the case of a damaged fuel line, it is essential to undertake repairs or replace the damaged section of the fuel line to ensure a secure and functional connection. If there is no injectors or they are inoperative, a comprehensive approach involves testing, repairing, and replacing the electronic fuel injection (EFI) main relay, EFI injector harness, and the electronic control unit (ECU). Engines equipped with cold start injectors might start when cold, run briefly, and then stop. The brief runtime indicates the fuel pump is working well, but there may be a fault in the main injectors or the injector control circuits. Our next topic is addressing potential issues in the cold start system. If the cold start system faces an electrical circuit fault, addressing the issues involves repairing or replacing the faulty electrical circuit. Similarly, if the thermotime switch is not functioning, it should be replaced with a new one to ensure proper operation. If the cold start injector malfunctions, the most effective resolution is to replace the problematic injector. When the cold start is initiated by the engine control unit (ECU), a faulty coolant temperature sensor could be the culprit. Replacing the sensor becomes necessary to rectify the issue. Moreover, if there is a fault in the electrical harness associated with the coolant temperature sensor and ECU, the recommended action is to repair or replace the harness or reliable functionality. In instances where the ECU itself is found to be faulty during a cold start, replacing the engine control unit is the appropriate remedy. By systematically addressing these potential issues, one ensures the proper functioning of the cold start system, allowing the engine to initiate and operate smoothly in cold conditions. The next task is addressing challenges in starting a hot engine. A fuel pressure gauge provides visibility into the fuel delivery system's effectiveness, ensuring sufficient pressure for optimal engine performance. Inadequate pressure can lead to inefficient engine operation. If dealing with a potentiometer type airflow meter, a sticking sensor plate can impede performance. The solution involves freeing the plate and removing any external foreign material. In cases of incorrect fuel pressure, a systematic test helps pinpointing the problem zone, followed by repairing system plumbing and replacing the fuel filter, pressure regulator and fuel pump. Leaking fuel injectors, particularly when the engine is stopped, necessitates the replacement of faulty injectors. Additionally, a faulty cold start injector or its circuit may cause unexpected operation during a hot start, leading to a semi-flood condition that complicates starting. If your fuel injectors are malfunctioning and not delivering enough fuel to the engine, your car's efficiency will be compromised, leading to increased fuel consumption. Tackling these issues systematically through inspection, testing, and targeted component replacements ensures the effective resolution of hot engine starting challenges.
Let's recap this topic. In this topic, you have learnt that in cases of incorrect fuel pressure, a systematic test helps pinpoint the problem zone, followed by repairing system plumbing and replacing the fuel filter, pressure regulator and fuel pump. When the cold start is initiated by the engine control unit ECU, a faulty coolant temperature sensor could be the culprit. Replacing the sensor becomes necessary to rectify the issue. Hello and welcome to this session on performing ignition timing check, spark plug inspection and replacement, identify and test Hall effect and optical sensors, trace and test sensor circuits. By the end of this exercise, you will be able to understand the process of inspecting distributor-less ignition timing, learn how to set ignition timing in an electronic distribution ignition system, demonstrate the proper procedure for removing, cleaning and inspecting spark plugs, gain proficiency in adjusting spark plug gaps for optimal performance.
Tools and equipments required: trainee's toolkit, timing light, spark plug spanner 1, a motor vehicle with distributor-less ignition, multi-scan tool, spark plug tester, air compressor. Materials required: emery paper as required, cleaning solvent as required, cotton waste as required. Inspecting distributor-less ignition timing is a crucial step in maintaining optimal engine performance. Before starting the engine, connect the negative and positive battery leads of the timing light directly to the battery terminals. Ensure a secure connection for accurate readings during the timing light operation. Connect the inductive pickup lead to the number 1 spark plug wire. The exact position on the wire is not crucial for accurate measurement, but it should fit between the gaps in the jaws of the pickup. Avoid pinching the wire between the ends of the pickup's jaw to maintain a free and unobstructed flow. The freedom of the spark plug wire is essential for the proper functionality of the timing light. These steps establish the groundwork for using the timing light effectively, promoting precise ignition timing measurements. Following these precautions ensures a seamless and reliable diagnostic or adjustment process when working on your vehicle's ignition system. Setting the ignition timing in an electronic distributor ignition system is a critical procedure for ensuring optimal engine performance. The process involves several systematic steps to accurately align the ignition timing, promoting efficient combustion within the engine cylinder. Direct the timing gun towards the timing tab on the engine. Verify the correct connection of the timing light by observing a flashing light illuminates from it. Some timing lights may require you to press a button or depress a trigger to initiate the light display. When triggered by the spark from the number 1 cylinder, the timing light flashes, illuminating the mark on the balancer. This illuminated mark is shown in relation to the timing marks present on the timing tab. However, as most engines typically demand a certain degree of advancement, you are likely to observe a timing mark positioned near the 10 degree before the top dead center. The flashing light from the timing light provides a visual reference for the precise timing, aiding in adjustments and ensuring optimal engine performance. Pay attention to the alignment between the balancer's mark and the timing tab marks to determine the current ignition timing setting. This process is integral to achieving the desired performance and efficiency of the engine. The process of removing, cleaning, inspecting, adjusting, and installing spark plugs is a crucial maintenance task to ensure proper engine performance. To start the procedure, the air cleaner assembly should be removed to assess the spark plug. High tension leads are disconnected from the spark plug, and the ignition coil assembly may be removed if necessary. Loosening the spark plugs, air blowing around them helps prevent foreign particles from entering the cylinders during removal. The spark plugs are then taken out from the engine cylinder. The next step involves checking the spark plugs using a standard spark plug tester. The first step in this process is to check the spark plug for carbon deposition, cracks, and damage. After inspection, the spark plugs are cleaned with a spark plug cleaning machine. Any wear or insulator damage is carefully examined. Following the cleaning and inspection, the spark plug gap is checked with a spark plug gauge. Adjustment is made according to the manufacturer's specification to ensure the proper spark plug gap. To check the ignition spark, the ignition coil is connected to the engine and high tension leads are reconnected to the spark plug. The plug is grounded, the engine is cranked, and the ignition spark is visually inspected. If there is no spark, then replace the spark plug. Finally, Install the spark plug to the engine and also install the ignition coil.
Let's recap this topic. In this topic, you have learned that if the ignition timing deviates from the specified range, proceed with a thorough examination of components such as the crankshaft position sensor, camshaft position sensor, throttle position sensor, and knock sensor. If any of these sensors are found to be faulty, replacement is necessary. The process of removing, cleaning, inspecting, adjusting, and installing spark plugs is a crucial maintenance task to ensure proper engine performance. Hello and welcome to the session on performing ignition timing check, spark plug inspection and replacement, identify and test Hall effect and optical sensors, trace and test sensor circuits. By the end of this exercise, you will be able to understand the principles and procedures involved in tracing and testing Hall sensors, optical sensors, and oxygen sensor circuits.
Tools and equipments required: trainee's toolkit, timing light, spark plug spanner, a motor vehicle with distributor-less ignition, multi-scan tool, spark plug tester, air compressor, emery paper as required, cleaning solvent as required. Let us begin the task by checking the sensor. To check your vehicle's wheels and sensors, start by parking on a flat surface. Look at the Hall effect and optical sensors for any loose connection, disconnected plugs or dirt. Use a scanner tool to connect your vehicle diagnostic system. Turn on the scanner and follow the on-screen instruction, choosing your vehicle's make, model and manufacturing year. Moving to the diagnostics phase, the technician selects the electrical ignition circuit and activates the auto defect feature on the scanner. Upon detecting faults, the scanner displays any present fault memory, allowing the technician to identify specific issues related to loose connections or defective sensors. Corrective actions are then undertaken, involving the rectification of loose connections or the replacement of sensors as indicated by the scan tool. Repeat the same steps to check all the sensor circuits and wire harness. Let us have a look at what optical sensor is. An optical sensor is a device that measures the quantity of light rays physically present and turns that information into an electrical signal that can be interpreted by a person or an electronic instrument. These sensors are crucial for contactless detection, counting, or positioning of parts with applications both internally and externally. By manually cranking the engine, the technician continues until compression appears on the gauge and the timing marks align. This ensures that the piston is at top dead center (TDC) and sets the foundation for precise ignition timing adjustments. Now let us have a look on how to trace and test the sensor circuit. The process begins by warming up the engine to normal temperature and then connecting a voltmeter between the EO213 terminal of the ECM coupler and the body ground. Maintaining the engine speed at 2000 rpm for 60 seconds, the technician observes the voltmeter. If the voltage consistently fluctuates above and below 0.45 volts, it indicates that the oxygen sensor and the closed loop system, including the air-fuel ratio feedback system, are in good condition. It signals potential issues such as intermittent trouble or a faulty ECM, PCM. If the voltage is stable, further checks are recommended for the BI circuit, looking for a short to the power circuit or a rich air fuel mixture. Subsequent inspections involves the MAP sensor, ECT sensor, fuel pressure, injectors and their circuits. If all these components check out, attention turns to the ECM, PCM and its circuit. Alternatively, if the voltage fluctuates as expected, the next step involves inspecting the EO213 connection from potential issues related to a lean air fuel mixture. If the connection is good, checks are conducted on the MAP sensor, engine ECT sensor, fuel pressure, injectors and their circuits. If the issue continues, then repeat the process and check potential BI circuit open or short or oxygen sensor malfunction. Further checks are recommended. If wire and connection integrity are confirmed, the final step involves replacing the oxygen sensor and rechecking.
Let's recap this topic. In this topic, you have learned that an optical sensor is a device that measures the quantity of light rays physically present and turns that information into an electrical signal that can be interpreted by a person or an electronic instrument. If the voltage fluctuates as expected, the next step involves inspecting the EO213 connection for potential issues related to a lean air fuel mixture. Subsequent inspection involves the MAP sensor, ECT sensor, fuel pressure, injectors and their circuits. If all these components check out, attention turns to the ECM, PCM and its circuit. Hello and welcome to this session on check charging system for the cause of undercharge, no charge and overcharge conditions. Let's start with this topic. On completion of this exercise, the trainees should understand how the battery charging indicator works during ignition. Trainees should examine and replace charging circuit fuse and indication light. Trainees should set up and utilize a multimeter to measure battery voltage within range.
Tools and materials required: trainees toolkit, multimeter, a motor vehicle, gloves, banyan cloth, emery sheet as required, cleaning solvent as required. Let us get familiar with the process of diagnosing problem with the charging system of a vehicle. Let's get this started. First, switch on the ignition of the car. it can done by turning the vehicle's key. If the ignition is on, then check the vehicle's dashboard for battery charging indicator light is on. Raise the RPM, that is number of revolution per minute, to 2000 and determine whether the charging light turns off. If the battery charging light is still on, then the following steps should be done. If the charging light does not turn on when the engine is turned on, always keep a close eye on the fuse of the charging circuit. If the fuse is functioning properly, that is, it is not damaged or broken, then check the condition of the charging indication bulb. In case if the bulb is fused or damaged, then replace the bulb. Make sure the connections are secure and not loose. In case if it is loose, tighten them. Conduct a thorough inspection of the wire to identify any frayed insulation or any other physical damage. These kinds of issues can be solved by using insulation tape or changing the wire. Till now, we have discussed the remedies for charging light is not on even after starting the engine. Next, let us discuss about the charging indicator light does not turn off while the engine is functioning. The remedies are as follows. When checking the drive belt, it is essential to ensure that the appropriate amount of tension is present, because the loosened drive belt will have a less contact on the alternator pulley, resulting in no power generation or less power generation. If all these remedies do not work, then check the battery's wire connections. Then the fuse needs to be examined, and if there is no issues with the fuse, then the multimeter needs to be attached to the terminals of the battery to check the battery's voltage. The multimeter's voltage is set to be measured in the range of 6 volt to 60 volt. It is necessary to check the battery's voltage while starting the engine. A voltage that falls within the range of 14.2 to 14.8 volts indicates that the charging system is operating properly. If the voltage is less than 14.2, that indicates there is a problem in the charging circuit or the alternator. Start the engine and check for the squealing sounds. The noise is occurring for the fact that there is a problem with the bearings or that the drive belt has not been fixed correctly. It can be fixed by positioning the drive belt correctly. It is necessary that you keep these points in mind in order to ensure that your vehicle continues to function without any issues.
Let's recap this session on check charging system for the cause of undercharge, no charge and overcharge condition. We learned that verify if the battery charging indicator lights on when the ignition is switched on. Start the engine and raise it to 2000 RPM, ensuring the charging indicator lights turn off. If the charging indicator light doesn't come on during ignition, follow steps to check fuse, bulb and electrical connections.
नमस्कार, मैं दिव्यांशी चौहान।
नमस्कार, मैं भगवती जबनाल। आप सभी का सीएससी कड़ी की तीसरी चर्चा में आपका स्वागत करते हैं।
हमने अभी तक बात की सीएससी सेवाओं के बारे में, जिसमें त्यागी सर ने हमें सीएससी का एक ओवरव्यू दिया। साथ ही हमने बात की
Today we will discuss about chemical earthing and its specifications.